Thanks for the nice introduction. Yes, when I checked yesterday in the evening, about 10% of the papers at that conference have the tag end-to-end in the title. And so this is also why we look into such architectures here. And to be a bit more specific, besides our entranced users for automatic speech recognition, there are attention-based encoder-decoder networks that are actually able to simplify the whole ASR processing compared to hybrid approaches, as they are able to directly transform acoustic features into text tokens. One example of encoder-decoder models is the so-called transformer model, which we can see here. I search for the pointer.
Try to show that points at the screen, I think.
Ah. Yep. There comes something. Okay. So yeah, the transformer model, we use it in a non-streaming fashion. So compared to the previous talk here, we use the whole feature sequence here at the input of the encoder, use some CNN pre-layers, and then we have an encoder that is made up of, in total, 12 encoder blocks. And for the decoder, it's step-by-step-wise processing in the transformer, where we use also the previous output token to make a prediction for the next output token based on these output token log probabilities. And yeah, the important stuff about the transformer is that it's based completely on attention layers that are inside of the encoder and decoder blocks, and that use no recurrency to model the temporal context in such models. One method that is quite prominent and well researched for hybrid speech recognition is stream fusion. Stream fusion can include additional channels, like from multiple microphones, additional features, or additional modalities, like, for example, audio-visual speech recognition into the ASR model. And for end-to-end based speech recognition, the optimal way of include additional feature streams is yet to be explored. So there's not much work on that, actually. And yeah, this is why we, in this talk, investigate the application of additional features and additional encoders to the transformer model, actually. As we can see here, for example, we have a second feature stream that is fed into an individual encoder and then also is input to the decoder blocks. So our contributions are that first, we explore the different levels of stream fusion. So there's early, there's middle, and there's late fusion, by including an exemplary phase-based feature vector here as the second feature stream. Second, we find a novel technique by investigating fusion, which is called multi-encoder learning, which basically uses the additional encoders only during the training process and not doing inference. So let's start to look into stream fusion. So the most obvious and the common solution to performing fusion is to perform early fusion on the feature level, which means we get a joint feature representation down here, where we have both features combined. Usually this can be done by something like concatenation. Here in our case, as we use CNN layers at the input, we just include the additional feature stream as an additional channel here. The good thing about this is that we barely add any complexity to the model, as we only get a few more parameters here in the first CNN layers due to the slightly deeper kernels. Then what we propose is actual middle fusion, where we use two completely separate encoders for each of the feature streams here. And as you can see here, the encoder outputs are then the input to each of these decoder blocks here. So let's have a look into these decoder blocks. There we can see that each of the encoders, the one comes from the left here, the other comes from the right, has its own multi-head attention function, which is used to attend to the encoder outputs. The outputs of both of these multi-head attention functions, after some residual connections are added here, are then combined in this red block, where we propose a weighted sum approach, which is basically just a simple linear combination of both of these outputs, which is steered by this hyperparameter alpha here. Also, we look into the concatenation method, where we simply take both of these hidden representations and concatenate them to a new feature, to a new hidden vector. So, late fusion, we target late fusion, even though it's cannot be compared to other approaches like Rover that are working on the output hypothesis. Here we take late fusion, call late fusion the combination of the output probabilities that we have here at the end of the transformer decoder. So there are two completely separate transformer models, so two encoder-decoder structures, and each one operating on its individual feature stream here. And the good thing about this approach is that this is completely modular, so you can basically train your models completely separately and then perform fusion of these models. But the fusion that we perform here is actually on a step-by-step basis in the decoding process. So we have this decoding time step L, and for each of these time steps, we take both of these posterior vectors and combine them also by some linear combination here. And what's then important, that the output of these combined probabilities is then, of course, there can be an additional language model included by shallow fusion. And then we get the output token, which is then also fed into both of the decoders for the next decoding step. So they have a common output token, which means that the fusion is actually in the decoding process. So it's not like we can have two completely separate decoding processes and then do the combination afterwards. Yeah, cool thing is it's the most modular approach, but as you might see, this also yields the highest complexity as we have two completely separate models here. So let's look into multi-encoder learning, which is quite new. Here we also use the setup like in middle fusion. So we have two encoders for each of the feature streams that is fed then into this decoder block. But for the multi-encoder learning, during training, we tie the parameters during learning, which means that both of these blocks here share the parameters, and which also means that both encoders have some influence on the learning of these weights. We also use the weighted sum here and bias the learning, or bias the weighted sum towards one of these multi-head attentions. And the trick is now that doing inference, we simply leave out one of these multi-head attentions, which means we only use one encoder then doing inference. And this then compares to the standard transformer architecture, which means that we don't add any additional complexity doing inference, which is pretty cool, I think. Yeah, now let's look into our experiments. We conducted experiments on two data sets. First is the smaller Wall Street Journal data set, and the other is the more reasonably sized Librispeech data set. For Wall Street Journal, we had outputs on character level, and for Librispeech, we used byte pair encodings created with sentence piece for about, I think, 5,000 output tokens. So pretty standard processing, actually. So the question is, what do we actually fuse? What kind of information? So as the blue features, we've seen them before, we use the standard filter bank features with 80 male coefficients and 3 pitch features appended. And as the additional feature, we take the phase-based features. Basically, these are ARGDMF features proposed by Lohrenz et al. And yeah, we had some previous publications where we can see that these features actually yield some complementary information because they have a really nice resolution of the formant frequencies here for voice sounds. Yeah, as acoustic model, we used for Librispeech, we used a large transformer setup. For Wall Street Journal, it was a bit smaller. And what's important to highlight is that we only use the attention-based loss. So there's no joint multitask, there's no joint training with multitask and CTC loss in addition. The language model that we employed is actually a 3-layer LSTM. One thing that's special for Wall Street Journal is that we use the look-ahead language model, which is pretty cool because it's it's a technique to learn your language model on word level, and then it can also output on character level, which is important for Wall Street Journal, where we use characters. So let's look into the results. First on Wall Street Journal. The single feature standard transformer is basically the standard architecture with the standard features for baseline magnitude, and there we reach quite good performance of 6.5 on the development set and 4.43 in terms of word error rate on the test set, which are pretty according to other authors' works actually. The phase features also get kind of good results, although they are 1% worse on the in absolute terms. But we think there might still be information in there where we can take some profit from. So let's look into the stream fusion methods. Early fusion yields some mixed results here, where we are only able to get a slight improvement on the eval set, but not on the def set. For the middle fusion approaches, the concatenation also didn't work out that well on the development set, but the weighted sum approaches were able to outperform on the development set. And especially for this last fusion T middle fusion approach, where we use the weighted sum and also tied the parameters for the fusion of the multi-head attention functions, we get quite nice results by not adding as much parameters to the whole system. Fusion late gets kind of good performance on the development set, but not on the test set, unfortunately. And it also uses the most of the parameters. So then let's look into multi-encoder learning. What you can see first here is that we don't add any inference complexity to the models, but we just enhance the standard architecture by using an additional encoder doing learning. And so if we compare these for the magnitude model, where we use the additional phase encoder doing learning, we get quite small improvement, but it comes at no cost, so that's quite nice. And for the phase features, we are actually able to get a reduction of 14.6% relative. Then we thought, okay, now we have two enhanced baseline models. Now we can also perform fusion based on these, and this is how we then achieved a good performance of 5.5% on the def set and 3.4 on the test set, which is compared to other works that are based on transformers on Librispeech, on Wall Street Journal, is a 90% relative improvement. So let's quickly look at the Librispeech results. These are pretty similar. So for fusion, we get nice results with the middle fusion approach that not adds as much complexity to the system. And also fusion late achieves a 10.3 relative reduction. And for the multi-learning approaches, it's the same. We get some consistent improvement by doing multi-encoder learning without adding complexity. If we combine both, we are also pretty good with 3.34% on test clean. So to sum it up, on stream fusion, we explored the different levels, and it turned out early fusion is not that good, late fusion is very good, but has a high complexity, and the middle fusion yields the best of both worlds in some terms. Then we explored multi-encoder learning, which gives you better performance at no additional cost doing inference. And combining both, we were able to achieve quite a good word error rate on Wall Street Journal for transformer-based approaches. So thank you for your attention, and I'm happy to receive questions now.
That's very nicely timed as well. So do we have questions? Well, there's one right down the front here, please.
Hi, my name is Radu Ionescu. Thank you for the nice presentation. I'm from the University of Bucharest. So I have two questions. The first one is related to CDC. So it wasn't clear why did you not use it? Can I rephrase? Do you think CTC would improve the results?
So the actual reason why we haven't used it from the beginning on is that we were not using ESP.NET, is the real reason, I have to say, because we use the Espresso toolkit, which is based on fair sequence, and there it's not natively implemented, let's say. I thought a lot about we definitely need to apply our methods with some CTC decoding because everybody does it and there's definitely some improvement by that. And I think it depends on the fusion scheme which we use, if you can really use a multitask learning with CTC, because the CTC loss is based on the encoder, and then you have to, for example, multi-encoder learning. If you have two CTC losses from two encoders, can you still apply this or doesn't it work? So yeah, this is future work, and yeah, we have some upcoming, hopefully upcoming publication on ASIU that is actually able to show same effects without using additional encoders at all. And this is something where we also plan to look into CTC. So yeah, nice suggestion.
Okay. Thank you. And the second question is related to, so the approach is multi-encoder learning. So I understand that the parameters are shared between the encoders. So that gives you the same number of parameters overall, but does it also give you the same processing time? As you have multiple encoders, I think you have to pass the data through like the two streams, right? Like
only doing training. So doing inference, it's really enough if you just take the one encoder and take the multi-head attention layers that have been trained commonly with both encoders. So,
but don't you increase the number of inputs and have to pass the magnitude and the phase?
Not doing inference. There you really just have the encoder, which is based on the standard features.
Okay, okay.
Yeah.
Thank you.
Okay, we have online question. I'm calling Ilya Sedunov.
Okay.
No, I'm not calling Ilya. He disappeared. So let me read question from the chat. Do you compare with an ensemble or similar transformers without different encoders?
The first row that we showed was actually the standard transformer that hasn't used any additional encoders. So I think there's the comparison for that. And the other one was ensemble learning.
Yeah, with an ensemble of similar transformers without different encoders. I think that was one question that was asked. Specific.
Okay. No, we haven't looked into that. But of course, I would assume if you just combine different transformers that were initialized differently, it's quite likely that you also get some improvement, I would say. But we think here, so we come from a fusion background, and we saw we have these two features that add something to the signal, but especially in Wall Street Journal, what we notice is there's quite of a variance if you use different initializations. And so there's also some different local minima that we will find in our loss, and maybe they combine to something better, I would say so.
Thank you. Any questions in the room? If not, I still have one online question, two actually. From Tituano Parcolat. Thanks for the presentation. Transformers are known to be particularly sensitive at early stages of training for ASR. Thus, adding more encoders increases these difficulties to converge.
Actually, this is also something that we address in our follow-up paper for this year's ASIU. We have the feeling that when we do multi-encoder learning and we share the parameters of these multi-head attention functions, that we actually, the one thing that we do is we somehow make this multi-head attention a bit more better regularized. We regularize the multi-head attention. And by doing this, it might be that it's actually possible doing learning, that there will be more learning in the earlier encoder layers. So I think maybe this is one of the reasons why this multi-encoder learning works, that we improve the multi-head attention so that the gradients can flow into the encoder better. So might be one reason. And actually we show something similar in our ASIU paper, which you can find on archive.
Okay, thank you.
Just about at time.
Okay, we are unfortunately or fortunately out of time. Next speaker, please. Thank you.